Hello friends, welcome again. In this lecture, we are going to discuss about the second type of payment, that is your rigid payment. In last lecture, we were discussing the flexible payment. किस तरह से flexible payment के अंदर हमने different layers को डिजाइन किया था. हमने पहले number of vehicle in terms of million standard Excel find out किए. फिर हमने देखा क्या वो million standard Excel number of vehicles हमारे fatigue या रेटिंग क्राइटेरिया में जितने नंबर ऑफ व्हीकल या जितने नंबर ऑफ रेपिटेशन हमें मिल रहे हैं उनसे कम है या नहीं. अगर कम है तो हमारा डिजाइन सेफ है. उन नंबर ऑफ व्हीकल और जो हमारा सीबीआर वैल्यू होता है इनको यूज करके हमने जो थिकनेस थी डिफरेंट लेयर्स की वो डिजाइन की. इन रिजिड पेमेंट वेस्टरगार्ड जो थे इन्होंने रिजिड पेमेंट का डिजाइन बहुत ही सिंप्लीफाइड वे में प्रोवाइड किया. So let us see what is rigid payment and how this is designed. The diagram which you can see here we have the rigid payment. Rigid payment के अंदर सामने जैसा कि आपको नजर आ रहा है एक कंक्रीट स्लैब लगाई जाती है. ये कंक्रीट स्लैब है. यहां से this is a concrete slab. It is placed over your subgrade जिसके बीच में कुछ ड्रेनेज लेयर प्रोवाइड कर दी जाती है. ड्रेनेज लेयर मतलब इफ देयर इज सब सरफेस वाटर इट कैन गेट ड्रेन्ड ऑफ. these मे बी ग्रैनुलर सब बेस या फिर सीमेंट ट्रीटेड सब बेस हो सकते हैं. इनके ऊपर हम अपना जो सरफेस कोर्स है जिसके ऊपर हमारे व्हीकल चलेंगे दैट इज आवर कंक्रीट स्लैब, ये हम प्रोवाइड करते हैं. As we have seen in flexible payment, we provide a bonding layer between the base course and your binder course. We provide a prime coat. अगर हम देखें हमारे बेस कोर्स और सरफेस कोर्स के बीच में, या फिर आप देखें कि बाइंडर कोर्स या बाइंडर मैकाडेम और सरफेस कोर्स के बीच में, तो उनके बीच में भी एक लेयर प्रोवाइड की जाती है बॉन्डिंग के लिए. दैट इज नोन एज टैग कोट फॉर टैकिंग. लेकिन इफ वी से इन कंक्रीट पेमेंट वी प्रोवाइड अ डी बॉन्डिंग लेयर. मतलब हम नहीं चाहते कि यहां पे जो लोअर लेयर्स हैं और जो हमारी कंक्रीट है इसके बीच में बॉन्ड बने. यहां पे डी बॉन्डिंग लेयर प्रोवाइड कर. What is debonding layer? It is a polythene sheet of around 125 micron. क्यों प्रोवाइड कर रहे हैं? Because there is concrete slab, a dense slab, और इसकी प्रॉपर्टी होती है कि ये टेम्परेचर वेरिएशन के साथ में अपने साइज को चेंज करेगी. Either it will expand or it will contract. अगर ये साइज को कॉन्ट्रैक्ट और एक्सपेंड करती है और नीचे बॉन्ड बना हुआ है बेस लेयर के साथ में, तो वो बॉन्ड उस एक्सपेंशन और कॉन्ट्रैक्शन को ब्लॉक करेगा. जहां भी हमारा एक्सपेंशन और कॉन्ट्रैक्शन फ्री नहीं होता वहां पे स्ट्रेसेस डेवलप होते हैं. इफ देयर आर स्ट्रेसेस देयर विल बी क्रैक्स. तो हम नहीं चाहते कि इन दोनों के बीच में कोई क्रैक्स डेवलप हो बिकॉज ऑफ फ्रिक्शन और बिकॉज ऑफ बॉन्डिंग. दैट्स व्हाई वी प्रोवाइड अ डी बॉन्डिंग लेयर. एक पॉलिथीन की शीट प्रोवाइड की जाती है. Now let us see various parameters which are very important in design of your rigid pavement. First parameter is your modulus of subgrade reaction. What is modulus of subgrade reaction? Modulus of subgrade reaction you have already seen in plate load test. It is actually the slope. What is this? It is the slope between your loading, or you can say stress, and your deflection. You know your loading versus deflection curve will not be a straight line, but at a deflection level of 0.125 centimeter, there will be some stress. And if we connect the origin with this point, the slope of this line is known as your K value. This K value act as a spring constant. मतलब हम मानते हैं कि जो हमारी सबग्रेड है वो एक डेंस लिक्विड है और वी कंसिडर इट एज अ स्प्रिंग. If you apply load, there will be deflection. So what is the spring constant of the spring? This is denoted by the K value, which is known as modulus of subgrade reaction. Now this K value can be calculated as P divided by 0.125. The unit of this K is kilogram per centimeter. So this is what K is, modulus of subgrade reaction. This is a very important parameter and we will use this parameter in design of rigid pavement. We have already seen different characteristic of this pavement, of this character of this parameter in plate load test. हमें पता है कि प्लेट लोड टेस्ट जो किया जाता है वो 75 सेंटीमीटर डाया की प्लेट पे किया जाता है. if we use different dia plate, how I can calculate this K value for that different diameter plate? So these things I already know from plate load test. If you want to revise, you can go back to the lecture and revise it and come back here to use this parameter in design of rigid pavement. Then another parameter is radius of relative stiffness. It is considered that whatever deformation is occurring in the slab, जितनी भी deformation slab के अंदर हो रही है, is equivalent to the deformation on the subgrade. जितनी deformation subgrade के ऊपर हो रही है उतनी ही slab के ऊपर हो रही है. So the relation between these characteristics is defined in terms of relative stiffness. So relative stiffness of slab with respect to subgrade is represented by radius of relative stiffness. And the radius of relative stiffness value is here. We know that stiffness of slab can be represented by this formula. If we compare it with or equate it with this stiffness value, then we can get the radius of relative stiffness. So L will be equals to EH cube divided by 12K 1 minus mu square raised to power 1 by 4. Here what E is? E is your elastic modulus for, we are talking about slab, means it is for concrete, which is equals to then we have your H is equivalent to your slab thickness. In centimeter. Then we have your K, you know, K is modulus of subgrade reaction. Mu is the Poisson ratio for concrete. This value you should remember, it is taken as 0.5 15. So this is what radius of relative stiffness is. देखिए किस तरह के सवाल पूछे जाते हैं. पूछा जाएगा radius of relative stiffness is directly proportional to your thickness of pavement. Yes, we know it is directly proportional to thickness of pavement. It is inversely proportional to your modulus of subgrade reaction. It is inversely proportional to your Poisson's ratio. So these type of relationships are asked in your GATE examination. 2 marks में direct is formula based क्वेश्चन भी आया हुआ है. तो ये फॉर्मूला गेट एग्जामिनेशन के लिए बहुत इंपॉर्टेंट है. नेक्स्ट पैरामीटर इज द क्रिटिकल लोड पोजीशन इन योर स्लैब. If it is your slab, there are some critical load position which need to be studied. सब जगह पे लोड मैक्सिमम नहीं होगा, लेकिन जहां भी मैक्सिमम होगा, अगर उसके लिए अपने पेवमेंट को डिजाइन करते हैं तो बाकी सब लोकेशन सेफ रहेंगी. So there are some locations which have maximum load. In the interior, there are few locations. First one is your interior of the slab. There will be certain kind of load which will be maximum. Then there are edges. These are edges and your corners. Their critical position or critical load position are interior loading, your edge loading, and your corner loading. So we will consider these three locations for calculating the critical stresses, and using those critical stresses we will design our pavement. As we see in the pavement, there is only a small area which resists the bending moment. So the small area which resists the bending moment is defined in terms of radius of resisting section. So the radius of resisting section, which is another parameter which we can use in design of, or which we will use in design of rigid pavement, is defined in terms of B. This radius of relative stiffness depends on your radius of contact area. If this radius of contact area is less than 1.724 times your thickness of slab, then we will use this first formula, which says is equals to 1.6 a square plus h square minus 0.67 times h. If it is not the case, means if a is equal to or more than 1.724 times h, then your radius of relative stiffness will be equivalent to your a value. This is another important parameter which you should remember. There will be direct question on these parameters. You may have a value and a h value, and you will be asked to calculate your radius of resisting section. So first you need to check whether your condition lies in this category or this category. Whatever the category, you can choose the formula and calculate the radius of resisting section. Now let us discuss about the stresses. What type of stresses does we see in a pavement? There are two types of stresses. One is vehicular stress because of the wheel load. Another one is climatic stress because of the change in temperature. The temperature change may be observed daily, daily temperature variation. Means there will be higher temperature on the top surface in the daytime, and in the night time there will be comparatively low temperature on the top surface as compared to the bottom surface. So this creates a temperature differential between your this creates a temperature differential between your pavement top surface and bottom surface. Because of the differential, there will be differential stresses, means different stresses. So warping stress is because of the daily temperature variation, whereas we know that in summer the temperature is high comparatively to the winter. So there will be temperature variation in terms of seasons, and that is known as frictional stress. तो टेम्परेचर स्ट्रेस विल अकर इन टू कंडीशन. एक तो हम जो दिन में टेम्परेचर का वेरिएशन देखते हैं उस समय, और एक जब हम टेम्परेचर का वेरिएशन सीजनल देखते हैं. तो लेट अस फर्स्ट डिस्कस द स्ट्रेस ड्यू टू लोड which is coming from wheels. Now we have considered that there are three critical conditions: interior, your edges, and your corners. Let us go back and discuss what will be the load condition if there will be wheel load on this page. Let us first consider interior. If we are looking at this point, this is your interior point. If load is applied here, or wheel is applying the load here, this beam will bend this way. Here you can see, because of this bending, there is compression on the top and tension on the bottom. So we will say, because of your vehicular load, there will be compression on the top and tension on the bottom in the interior area or interior slab. What is the critical load here? Compression is never a problem in concrete, but tension is. So we are looking at the tensile stresses which generates due to various load combinations. Looking at the edge, if my wheel is at the edge, if I am looking at the edge, the scenario will be same as there will be bend, compression at the top and tension at the bottom. This is your interior area, this is your edges. But at the corners, if wheel are acted on the corners will bend like this, similar to a cantilever, because they are not continuous, they are not held anywhere. So there will be tension on the top and compression the bottom. So in this case, we can see that the compression, the tension, so we are looking at the tension value. We are looking at the tension value, and this tensile stress can be calculated by these relationships provided by Westergaard. Westergaard provides these relationship for stresses for interior, for edge, and for corner location. This is at interior, in the top surface. Is it top? No, it is the bottom surface because tension is at the bottom. Not the top surface, it is the bottom surface. Then it is at the edges in the bottom surface. Why bottom? Because tension is at the bottom surface of the slab. The bottom. एंड फॉर कॉर्नर्स हमें पता है कॉर्नर क्योंकि कैंटिलीवर के जैसे बिहेव करते हैं, तो कॉर्नर में जो स्ट्रेसेस आएंगे टेंसाइल स्ट्रेसेस वो आएंगे टॉप में. टॉप सर. So these relationships are important. In your GATE examination, it is directly asked the relationship between your stress and your wheel load. Between your stress and your thickness of slab. Between your stress and your modulus of subgrade reaction. The question is asked how the stress and modulus of subgrade are related. We know that in this equation there is no modulus of subgrade reaction, but this value L, this uses the K value for calculation, radius of relative stiffness. So how we will describe the relation between the modulus of subgrade reaction, which is in terms of L, with your stresses? This is important. So better you remember all these formulas so that these kind of relationship can be easily solved in your examination. Then there are temperature stresses. We know that temperature stresses are of two types. First one is your daily temperature stress. This is due to temperature differential at the slab surface. Slab. What happens is a slab and it is daytime. Temperature at top will be higher because of the sun. Because of the sun, temperature will be higher at the top, and comparatively the temperature variation will look like this. There's T1 temperature or T temperature at the top, T B temperature at the bottom, and there is some difference in these temperatures, and the difference in T top minus T bottom is known as temperature differential. Known as temperature differential. So because of this temperature difference from top to bottom, these stresses generate. Now let us see why these stresses generated. If I have a slab, let us say this is my slab, this is daytime. Daytime, the temperature at top, this is day, write it here, day. For this day, the temperature at top will be more than temperature at bottom. Where there is higher temperature, there is expansion. So at the top, there will be expansion. Comparatively, at the bottom, there will be expansion, but in less amount. So this beam will bend in the plane like this. Because if it is higher temperature at the top, there will be more expansion at the top as compared to the bottom. So because of this shape, what my center would like to do, my center would like to come back because of its weight. And because of this weight, resistance to this expansion occurs. भाई देखो, अगर आपको अलाउ कर दिया जाए कि आप टेम्परेचर के साथ में बिल्कुल एक्सपेंड हो जाइए, तो कोई प्रॉब्लम ही नहीं है, देयर विल नॉट बी एनी स्ट्रेस. बट इफ यू आर प्रोवाइडेड अ रेजिस्टेंस, अगर आपको एक कुर्सी में बिठा दिया जाए जिसकी स्ट्रेस कम हो और उसमें कहा जाए आप जितना फैल के बैठो बैठो, बट बिकॉज ऑफ योर एक्सपेंशन यू हैव सम बाउंड्री. अब एक्सपेंड होना है, एक्सपेंड होने नहीं दिया जा रहा है, तो देयर विल बी स्ट्रेसेस. सिमिलरली हियर देयर इज रेजिस्टेंस ड्यू टू द सेल्फ वेट. यहां पे ये फैल गया बिकॉज ऑफ हायर सरफेस एरिया. दिस वेट विल ट्राई टू कंप्रेस इट बैक टू इट्स ओरिजिनल लेंथ. क्या किया जाएगा? इसको कंप्रेस किया जाएगा. सो दिस देयर विल बी कंप्रेशन at the top. There will be compression at the top. This compression. And at the bottom, there will be tension. Because we want to get back to the original shape. There will be tension. So in a condition where, or in a daytime, there will be compression at the top and tension at the bottom. If it is night time, during nights, this slab has a reverse temperature gradient. The T at the top will be actually less than T at the bottom. Now with the sun going down, the temperature at the surface will also decrease. But it will not affect directly to the temperature at the bottom. The bottom temperature relative to the top temperature will change slowly. धीरे धीरे चेंज होगा. अब नाइट टाइम में जैसे सूरज कम हुआ, टॉप सरफेस का टेम्परेचर कम हो गया as compared to the bottom. Now what will occur? The bottom will expand. How? The bottom will expand such a way that it will form this kind of shape. Because the temperature at the bottom is higher, the expansion at the bottom surface will be higher, and this will be registered by the weight of this pavement. This weight will try to compress your bottom so that to bring it to the original position, and will try to expand or provide tension at the top. So there will be tension at the top and compression at the bottom. These type of stresses which are generated in daily variation is known as warping stress. Warping stresses. The other type of stress which we see with the seasonal variation of temperature there is no differential in the slab. The complete slab will either expand or contract. There will not be any differential in the top surface and the bottom surface, either compression or tension in complete slab. Now look why this compression or tension is coming. This is my slab. This is placed over a granular surface. Now with increase in temperature, my slab will try to expand. So I am talking about summer. We know that summer has comparatively higher temperature. So in summer, this slab will try to expand. But as we have placed this slab on a granular material, there will be friction. And friction will try to stop this expansion. And you know that whenever there is any resistance in expansion, then only there is generation of stresses. So we can see that because of what this slab is trying to do, the slab is trying to going out, but what the friction is doing, it is resisting it in opposite direction. So there will be stresses in this way. The slab is trying to move out, but the friction is resisting inside. So there will be compressive stresses. So in summer, the complete the complete pavement will be having compression. And in winters, you can already imagine this thing. In winters, the opposite going to happen. This is a slab. This will try to contract, but the friction below will not allow the slab to contract. So it will resist the contraction. The slab is trying to contract. So there will be tension. There will be tension. So this is why we provide a debonding layer in order to reduce these type of frictional stresses. So these are the temperature stresses which we can see or observe in the pavement. And in order to reduce the cracking, we provide some joints. We are going to discuss about the joints in later session. Now let us see the calculation for the warping stress. Whatever stress is going to occur here is your warping stress. Now, if we consider our slab, x direction, this is your Ly, this is your Lx. So for this slab, the stresses at the interior is provided by this relation, where your E is the modulus of elasticity of concrete, which is taken as 10 to 10 raised per 5 kilogram per centimeter square. Your mu is Poisson's ratio. Your T is the temperature differential from top to bottom, and your epsilon is your coefficient of thermal expansion of concrete, which is actually taken as 10 into 10 raised per minus 6 per degree Celsius. You can write it as 10 raised per minus 5 per degree Celsius, but it is the way in which it is written. The two constants Cx and Cy, these are known as Bradbury's warping stress coefficients, and these can be calculated using this curve, where we know that this Cx and Cy depends on your Lx by L and Ly by L. What is L? You know that the L is your radius of relative stiffness. So does your warping stress depend on your radius of relative stiffness? Yes, because the coefficients, the Bradbury coefficients depends on this L value. So yes, our warping stresses depends on, and how these are dependent, you can create the relationship. Now we put mu equals to 0, we will reach to the warping stress value at your edges. This is for edges, this is for interior area, and this is for your corner. We know that what are type of stresses are there: compression at the top, tension at the bottom in day, and tension at the top and compression at the bottom in night. So these are the warping stresses which are produced in your slab because of daily variation of temperature. You should remember that Poisson's ratio, the value of Poisson's ratio is taken as 0.15. The temperature differential, let us talk about this. The maximum temperature differential occurs during the day in the spring and summer months, because the temperature at the top is very high and the temperature at the bottom is relatively cool. During the midday of summer, the surface of the slab is exposed to sun, and this warms faster than the subgrade, which is relatively cooler. This creates a temperature differential. रात के समय पे जो सरफेस होती है वो ठंडी हो जाती है as compared to the subgrade, and because of this variation there is temperature differential. It is said that at night times temperature differentials are one half the daytime temperature difference. रात में जो टेम्परेचर का डिफरेंस है वो कंपैरेटिवली हाफ होता है जो दिन में टेम्परेचर का डिफरेंस हो. The actual temperature differential depends on the location. Yes, we know that, because temperature variation also depends on the location. The temperature differential is expressed as temperature gradient per mm of thickness of slab, and it varies between 0.67 to 0.1 degrees Celsius per mm. For different thickness and different locations, for different thickness and different locations, this value is given. So it is said that this value is 0.67 to 0.1 per degree Celsius, degree Celsius per mm. For various thickness, we multiply these value by thickness in mm, and we can get the differentials from the code. This provision is provided in your code, which is IRC 58. We have the latest version of IRC 58, that is 2015. So this design is based on IRC 58. So for all the states, different areas, we have the temperature differential for different thickness of slabs. This will help you to calculate the warping stress. Then there are frictional stresses. We have already discussed the frictional stresses. The slab, with increase in temperature in summer, tries to expand, but there is restriction. It wants to expand, but there is restriction. For summer, there are compressive stresses, and it is considered that these stresses are studied for half of the length, because the other half has similar type of compressive stress. This is due to the seasonal variation of the temperature. Now, if we want to calculate this variation, we can say that this expansion or the tensile stress in the pavement is actually equal to the friction applied. So friction value can be given by M. This is resisted or this is equivalent to the strength. This is equals to the strength of this section in tension. If we are seeing this section, it will try to contract, and if there is another section nearby, it will also try to contract. In winters, in summers, they'll try to expand. So this expansion and contraction will provide or will generate tensile forces. So the frictional resistance is equal to the this tensile forces or tensile strength of the pavement. This tensile force is equal to the permissible tensile stress on the surface. Here, permissible tensile stress on the surface into the surface area, the width, pavement. So the friction value, friction coefficient multiplied by the total area here, the friction coefficient multiplied by the weight. The weight can be calculated by multiplying the volume with the unit weight. The volume is your width multiplied by your height multiplied by half of the length of and this is the stresses which are occurring here. So these are the stresses level B. So if we say these stresses multiplied by your unit weight of concrete, this will be equals to your frictional stress multiplied by L multiplied by your concrete. So this is the formula can be used in order to calculate the frictional stresses. Frictional stresses in corners, in interior, and in at the edges. This will be seen. We are very much interested in the tensile stresses, which occurs during the. When does these tensile stresses are occurring? These are occurring during the winters when your object or the pavement is trying to contract. That's why we provide your contraction joints. Now let us see various load combinations and we find which load combination is critical for design. Due to wheel load, we know that the interior has minimum stress because it is continued in both the direction, whereas corners which are having tension at the top has maximum stress because of the discontinuity, and the edges have intermediate range. While for temperature variation, the interior has your maximum stress. Your stress variation in compared to the temperature, it is like this. Means at the corners, the temperature stresses are usually kind of zero, and at interior it is maximum. So corners have minimum temperature stresses, the interiors have maximum temperature stresses. So in order to design a pavement, we should consider the edge region because it has intermediate stress in terms of temperature as well as in terms of wheel load. So we will consider the combination of wheel load and temperature stresses to be critical for your edge region. We design it for edge region, but we check it for corner region so that all the combinations are safe. Let us discuss various combinations and find out which combination is the most critical. For location, edge, interior and corner, let us discuss the load stresses. Load stresses because of your wheel load. Wheel load at the edges, we know that at the top it is a compression, at the bottom it is a tension. Similar for the interior, it is a compression at the top and tension at the bottom. But for the corners, where it behaves like a cantilever, there is tension at the top and compression at the bottom. For warping stresses at daytime, you can go back and check. Warping stresses at the daytime, there will be similar stress on the top for edge, interior and corner. So warping stresses at the daytime, the top surface is expanded and the weight is trying to compress it. So we have compression at the top at the day, at the top, compression at the day, and compression at the top in edge, interior and corner, tension at the bottom. At night time, we know that the temperature differential is reversed. So in this condition, at night, the temperature is higher at the subgrade level and comparatively lower at the surface level. So at the night time, the top surface will be having tension because the bottom is expanded and it will be compressed because of the load. So there will be tension at the top, compression at the bottom, tension at the top, compression at the bottom, tension at the top, compression at the bottom. Frictional stresses are similar in all the three areas. Means if it is a tension, if your slab is trying to expand, then the friction is trying to compress it. So for summers, there will be compression throughout. And for winters, there will be tension throughout. So we need to find the load condition which is critical. We want to see where always there is tension. We also know that at corners there are no or very negligible frictional stresses. So we can ignore these values. And from these combinations, we can say that for bottom or for edges, bottom, bottom, and bottom. So we can write that for interior, for edges, critical load combination is stress, this load stress at edge, at bottom, plus warping stress at day, or we can write the combination as for edge, combination should be a winter afternoon stress will be critical. So this is most critical combination for edges. If we talk about the interior, the most critical cases or the combination is the same when in a winter's day. In a winter's day, there is tension at the bottom because of loading also. So this combination is holds good for your interior portion too. Finally, for the corners, we have the critical combination as your top in any night, your corners have tensile stresses at the top in night. If you want to consider, you can say it is the winter, but as you know, the frictional stresses are negligible, so you can ignore it and you can write this combination. See, in order to save your payment with the damage because of these stresses, these combinations, what we do, we provide joints in the direction in which we are moving. The direction in which we are moving on this road is known as longitudinal direction. So the joint provided in the longitudinal direction or in the direction of traffic is known as longitudinal joint, and the joint which are provided perpendicular to this direction are known as transverse joint. So this is a slab jointed with longitudinal and transverse joints. In transverse joint, we have expansion joint, which are generally provided of around 140 meters. Then there is a contraction joint, which are usually provided at a distance of 4.5 meters. And then there are construction joints. Whenever you stop the construction of a day and then begin the construction for next day, you provide or there is a joint. Expansion joint provides you a cushion or the space in order to allow the expansion of the slab. The expansion joints, expansion joints are designed such a way that it allows the expansion and allows the compression of the filler material into this joint. Contraction joint are actually not proper joints. These are the locations where localization of cracks are done. We provide half a crack in the slab so that the cracks gets generated from this point only, and fill this with the help of filler so that the cracks generate at this location only, because somewhere there will be a crack. So let us provide a location where there should be crack. Let us not allow anywhere to any location to generate contraction crack. In this diagram, you can see this is the direction of traffic. In the direction of traffic, these are your longitudinal joints. These are your transverse joints. Expansion joints. Expansion joints are separated with the maximum separation of around 140 mm. There are joints which are provided in between the expansion joints, and they are known as your contraction joints. And contraction joints has a spacing of around 4.5 meter. There are bars which are provided in longitudinal and the expansion joints. The bars which are provided in the longitudinal joints are known as your tie bars. There may be a question which is asked that tie bars are provided along the direction of the traffic or transfers to the direction of traffic. Now in this diagram, you can easily see that the tie bars are provided on the joints which are along the direction of the traffic, but the alignment of tie bars are such that they are provided transfers to the direction of traffic. Similarly, the expansion joints are provided with dowel bars. These dowel bars are actually provided along the direction of traffic. These tie bars does not act as load transmitting bars. means it does not require to distribute load from one slab to another slab. But the dowel bars are designed to transmit or transfer the load from one slab to another slab. So let us discuss about these joints and bars. Now the expansion joint are designed in order to provide expansion which will fill the gap or fill the half of the gap. Let us say this is your expansion joint provided between two slabs. Definitely there will be a dowel bar, but right now we are not discussing about the dowel bar. Let us say this joint spacing is delta. What we are saying, we are allowing this space to be filled half, means 1/4 of expansion is allowed here and 1/4 expansion is allowed here. Still a gap of around delta by 2 will remain. We need to fill this gap with the filler material, some kind of polymer, some kind of rubber. So we will allow the compression of this filler material by half of its width. So we know that the change in this spacing will be delta by 4. Now let us calculate. We know that the change in length because of temperature can be calculated delta by 2. The change in length of the slab due to temperature is equals to L alpha T. This we know from your strength of material of or mechanics of solid. So here you can calculate the width or the opening of your expansion joint, or from here only you can calculate the distance between these expansion joint which are to be provided. So the next one is contraction joint. Contraction joints are provided in order to allow the contraction at a certain section. So there are two conditions for contraction joint. One, if there is any reinforcement provided or if there is no reinforcement provided. So let us say if no reinforcement is provided or no steel bars are provided. If no steel bars are provided, there is a slab. It will crack from here. We want to calculate the length or the spacing where this crack is going to. This crack, if there is contraction, means it is cause of tension at this location. So we know that this tension will be registered by this friction. There is contraction, this will be registered by the friction. So how much tension is allowable? This allowable tensile force in your concrete, this is registered by your frictional force. Frictional force to frictional force by area. So this frictional force is acting at the bottom and this tensile force is acting at the surface. So let us calculate. F is equals to your volume into unit weight of your concrete. What is the volume? Volume is length of your, means total length between two cracks. This is the spacing length of your contraction joint, multiply the width and the height, multiply the unit weight of concrete. The G is itself converted by density of concrete multiplied by G into unit weight. Okay, so don't get confused about this G. Here we have the area of this section. This area of section is B cross H. So we will subtract it, and this sigma value will be, okay, so this L here is L by 2, because we know that half of the concrete pavement is compressing from this direction and half is compressing from this direction. So the length of the effect of this friction will be applicable on half of the length. So this sigma value will be F multiplied by L by 2 into gamma C. Now you can calculate the length of or the spacing between these concrete joints or contraction joints as 2 sigma by F gamma. This is how you can calculate. If some steel is provided, this tension will be resisted by, we will say this will be resisted by the steel. So the force, frictional force will be area on that area is equal to the resistance to the friction provided by the steel bars. So we can write that AST, area of steel in tension, multiplied by sigma ST means permissible stress in the steel in tension will be equal to your frictional force. This is F dot mg. Let us directly write mg is equals to LC by 2 multiplied by your E H gamma C. Now LC value is equals to, you know how much steel is provided, you can calculate here 2 times of AST sigma ST by F V. You can also calculate the spacing between these bars. So spacing between whatever steel you are providing can be calculated by, for 1 meter, AST multiplied by pi by 4 d square. This is how you can calculate the spacing. So this is how you will calculate the spacing between your contraction joints. Spacing between your contraction joints in 2 conditions: one when there is steel provided, another when there is no steel provided. The tie bars are provided in your longitudinal joints, and dowel bar are provided in your expansion joints. So let us discuss about the tie bars. Tie bars are actually provided in order to hook the 2 slabs together. These are the 2 slabs. The tie bar will help to tie these together. So essentially these bars are provided as deformed bars. When you will study RCC, you will learn about deformed bars. You have seen the TMT bars or general bars, reinforcement, which are used here and there. You have find these lines like this on the surface of your bar. This is known as deformed bar. If these lines are not provided, it is a smooth rod, then there will not be any surface bonding between your bar and your concrete. That's why these deformation are provided. These are placed at a larger spacing as compared to dowel bar, because these are not your load distribution bars, and the maximum dia is limited to 20 mm. The spacing should not be more than 75 centimeter. So let us see how we can design these bars. the similar value will be used, or the similar direction will be used in order to calculate your AST. This is registered by the friction, because these are bonded, and the bonding will provide a grip, and due to contraction or expansion there will be the variation in length. Let us calculate this. For 1 meter length, how much steel can be provided? This volume, this is for the frictional coefficient. So you can calculate AST from here, the amount of steel which is to be used. You can further assume the diameter and calculate the number of bars which can be used in this arrangement. Here the F value, it is very important. The F value which we are using, this is equals to 1.5. Already in transportation we have studied two F values earlier. One was friction between wheel and your surface in longitudinal direction. Other was friction between your wheel and the surface of pavement in lateral direction. And here this is the friction between your pavement or the concrete surface with the subgrade or your base. Now if you want to calculate the length of tie bar, this length of tie bar can be calculated using, or it is equals to 2 times of your development length. Let us talk about development length. You are going to study this topic in RCC, but let us discuss it here. Whenever there is a bar which is having a bonding with the concrete, the total length which can be embedded into this concrete is known as development length. And this can be calculated using your tensile stress or strength of bar and your bonding stresses. So your bonding stresses is applicable on a length, this is LD, and on the circumference. If I am putting this bar into this concrete, this much length which is inside will provide the definite bond, so that if I stretch or provide a tension here, this does not come out. There will be condition when this steel will fail in tension or there is loose in this bond. When this occurs simultaneously, then we say this is what we could do. This much length, अगर स्टील ही फेल हो गया तो ये लेंथ कितनी भी प्रोवाइड करो, हमें उससे कोई मतलब नहीं जब स्टील यहीं से फेल हो गया। तो बॉन्ड फेल नहीं होना चाहिए। तो बॉन्ड कब तक संभलना चाहिए? जब तक ये स्टील फेल नहीं हो। तो बॉन्ड स्ट्रेंथ क्या हुई? द अलाउबल बॉन्ड स्ट्रेंथ, ये बॉन्ड कहां बन रहा है? इसकी सरफेस पे। सरफेस इज द सर्कमफ्रेंस इनटू द लेंथ। Phi is the dia of the bar. This is the surface area where this bond stress will be applicable. And when this force is equals to the tensile force equivalent to the failure, this is the permissible tensile force, multiply this is applicable on the diameter of this steel. Now let us calculate the length of development. Length of development is equals to, let us move this pi by pi, is equals to, and 1 phi by phi is sigma st to the diameter divided by 4 times sigma b, let us write as b, sigma bond. So this is length, development length inside one of the slabs, and the length of tie bar is equals to 2 times of development length. Finally, let's discuss about the dowel bar. There is a design, proper design for dowel bar, but it is not required for GATE examination, because GATE examination will not ask the proper design, but the formulas are important. For double bar, the purpose of double bar is to provide effective load distribution. Why double bar are provided? If it is a joint, double bar are provided at expansion joints. My traffic flow is in this direction. If my wheel is here, this will move with a proper deflection. So this is the deflection which I can see because of this bar. Now, whenever this deflection occurs, there will be a lot of impact on this next pavement, and with time this will deteriorate. So what we do, if this is delta, we try to provide this load equally distributed in this pavement, where if this loading occurs again, there will be comparable deformation in both the pavements. So there will be, the deflection is delta. Now the deflection is delta by 2 here and delta by 2 here, and the load whatever here is, it is transferred. The double bar are not bonded in both the slabs. It is bonded in one of the slabs, and in other slab it is left loose with a kind of arrangement. Pillar is provided, finally metal cap with cotton is provided, but it is loose here in order to allow for, the expansion joints are provided in order to allow the expansion. If we bond this layer, there will not be expansion, there will be cracks. So to allow that expansion, we have to provide it, and there should be load transfer also. So it is considered that the load transfer is around 40% to from first slab to second slab. These bars are designed for shear, bending and bearing all the stresses. The maximum length of double bar is generally 0.5 meters. For a spacing of around 200 mm, the diameter can be taken as 25 mm, and for a spacing of around 30 mm, for a slab thickness of 20 centimeter, the diameter can be taken as, okay, for a 25 mm diameter, the spacing can be taken as 200 mm for 15 centimeter thick slab, and for 20 centimeter thick slab, the spacing can be taken as 300 mm. So this is how you can design a double bar. You should remember these specifications which we have provided for double bar, and the requirement of double bar, the arrangement of double bar. The design itself will not be asked. So this is enough from the rigid pavement design. We will see some of the questions, the practice questions, in next lecture from your pavement design and your from pavement materials. So till then, thank you so much.